I think so. Just check if the audio is on the right source. I hit the rest of it. Yeah, it is on. Yeah, I've hidden it. I cannot see it anymore. You can go there on the it's there on the top. It is there. It is there. So I think we're almost complete. We can start this lovely session about the hidden master transfer.
The first presentation is by Niles Savant, and then it's relevant to Lattice Boltzmann for porous media reactive flows with application to solid oxide fuel cells.
So thank you for the kind introduction, and thank you everyone else for attending this talk and also the conference. So I'll briefly talk about one possible approach to do reactive flows in to do reactive flows with the lattice Boltzmann method. So yeah, so this is where we begin from, unfortunately, but yeah, so we started with this. So we had this lattice Boltzmann method, which I developed as a PhD student. It was not for porous media, but it was for generic flows for combustion. So basically, what we did was we had this model. So it consists of three sets of equations. So basically, we have one equation, like just one lattice or one population for the total mass and total momentum of a multi-component fluid. Apart from that, there is another equation for energy. So this energy equation, it represents the total energy of a multi-component system of fluids. And let's say we have m species. Then for each of the m species, you have one equation. So you have m species equations for the species dynamics, basically. So yeah, it's not too complicated. So you what happens is you have this blue populations which are for the mass and momentum. So they conserve the total density rho and the total momentum rho u of the fluid. And whereas you have a G population which conserves the total energy of the sum of the components, like the fluid. So you have this rho summation of GIs rho E, and this U, which is internal energy. It contains both the sensible heat as well as the heat of formation. And then we have this M populations. So each of the M populations, it conserves the density of its own component. So like for the like F the third F conserves the density of the third component, for example. So why did we do this, and what was novel about it? First of all, was the thermodynamic consistency, and we tried as much as possible to have no free variables in it. The system is nicely coupled both ways or all three ways. And then there is also an element of reduction. So one way of doing this would be also to have m equations for energy, but we do not have them. We have a single equation for energy. So there was a reduction component of it. The third thing was it was fully compressible, as I will show you in the next slide. You can verify it from the resulting macroscopic equation. So it is a model that is ready for doing some possibly transonic flows. Another thing is because this U, it contains also the heat of formation. So because of that, we do not have a different source term for the heat of reaction as such. Yeah, another thing, yeah, and then the usual advantage of LBM. So if it is fully in the LB framework, so we have less problems of conservation and so on. Than if you would have had a hybrid method, which is part LB, part FTM. So another interesting part, or rather my favorite part, was the diffusion. So rather than having a fixed diffusion, we were able to put Stephen Maxwell diffusion. So it's a pairwise diffusion where each component gets to interact with all other components. Because of it is a more natural way to represent diffusion, and the resultant equations would then not have any correction velocity, for example, which you would have in fixed diffusion. So going on to the macroscopic picture, now this is how the equations look like roughly. So you have on the left first, you have the continuity equation, momentum, and then energy. the usual pressure tensor. You have a heat flux with a component for the interdiffusion heat flux. So this is the heat flux because of the mixing of the species. So this is the hydrodynamic system, and on the right hand side you can see uh, the species dynamics. So equation for the species. So you have a convection diffusion reaction equation, and then the diffusion velocity satisfy the Stephen Maxwell constitutive relation. So on the right hand side, you can see the pairwise interaction of species, and on the left hand side you also have barodiffusion. So you also somehow account for the effect of pressure gradients on the diffusion of species. So with this base model, we were able to do a lot of interesting things. So for example, Kelvin-Helmholtz instability in 3D, and then we also did some combustion problems. For example, open flame in a microcombustor. So this is some 9 species hydrogen oxygen setup. Apart from that, we were also able to do some detonation, but only in 1D, up to Mach 2 or so, 2.1. And then we had the Stephen Maxwell test where we successfully showed that the model recovers uphill diffusion and osmotic diffusion. So going on from here, what we have to do now is we needed a model for porous media. So we go with the REV approach, which is this representatory elementary volume approach. So what you do in this is you do not really resolve the microstructure of the porous media. You have some factor phi, which is porosity or the void fraction, and then this phi becomes as a parameter in the linear equation. So I've put in green what I've changed. So basically, we needed to put this porosity, like the void fraction, and then we also anticipate doing some reactive flows in porous media. So we have mass interchanging from the adsorbed phase to the gas phase. For that, you need some source terms than in the mass and the energy equation, because you're only tracking the fluid phase, and then as the mass and energy interchanges, you need to account for it. And for species dynamics, we also added Knudsen diffusion, so we could go to the dusty gas model, and we have the effect of interaction with the wall. So yeah, so this is how it looks like. So for example, you can see the forcing term has changed a bit. Now we have an additional component to take care of the wall interactions. And yeah, there are some changes to the moment. So for example, the zeroth moment then is no longer rho, it's phi times rho. The first moment is not changed because it is something like phi times rho multiplied with u by phi, so that cancels out. Yeah, and you have some this porosity going on in the zeroth moment of the energy and also for the species. And this also has consequences for the higher order moments, like Q or P, for example. But yeah, I didn't want to put too many equations. And yeah, but it has consequences for higher order equilibrium moments also. So now let's see what we can do. So these are the resultant equations. Then you have mass, you have the continuity equation, then you have momentum energy as usual. So the momentum term in the net momentum equation, you will have a penalization term like this force density kind of term. So this is the because there is a species. So I think it makes sense if we go from right to left. So there's a consecutive there is a constitutive relation, and that has an additional term now, which is a retardation due to the interaction of the species with the wall. And then if you take the net of this equation, if you sum over a, you see that the net momentum will not be conserved. There will be a net forcing to the momentum, which gives some negative force because of the wall interaction. So we account that in the we remove it from the momentum equation basically. Yeah, and then Here's as we see these five factors go all around the porosities, then in continuity, it's in some places in momentum and energy. Also, it comes in the stress tensor. Also, for the heat flux, what we assume is that the solid phase and the fluid phase is in thermal equilibrium, and we do not solve the conduction equation inside the solid phase. So this heat flux only applies to the void fraction of the fluid. And then going for the next, what we do is we need to validate this. So this is a very nice setup on the left hand side. It looks quite complicated, but it's not so much. So basically, you have two cylinders, there's G1 and G2. So you fill in G1 with some gas, let's say helium. G2 might have another set of gases like neon, argon. You let them flow through the capillary diffusion cell. So what this capillary diffusion cell is, it's just a bunch of capillary tubes held together, and we know what the diameter of the tube is. And basically, you let this thing diffuse. So there are two interactions inside. So as the gases interact with each other, they diffuse, of course. So um, that is interaction of one gas component with the other, and then there is another interaction, which is the interaction of the gas with the tube, with the walls of the tube, for example. So yeah, the first part is associated with molecular diffusion, and the wall interaction is the part which is associated with the Knudsen diffusion. And on the right, we can see that something like that we can easily do with the 1D simulation, basically. So what happens is this D0 is the diameter of the capillary tube. That comes as a parameter inside. That comes as a parameter in your model. So you have 1D simulation, there are no walls, and gives a pretty good agreement with the experiment. So on the right hand side, what you see is this same experiment. It has been performed for a wide range of pressures. So the highest point is like zero point 0.4 atmospheres. So uh, yeah, I think 0.44 million. And the leftmost part is just a 60 Pascal. And we see we have a pretty good agreement, except on the 60 Pascal test. So these are yeah, basically, sorry, I forgot to say. So what we have plotted is um, molar fluxes versus pressure. So molar fluxes of each of the components. And then going to a more complicated setup. So this is a solid oxide fuel cell. We don't bother with the entire fuel cell. So we just go to the middle region where you have electrolyte layer, and then the immediate layers of the porous electrodes. So we can again do a 1D simulation of this. Yeah, but we need a little help in this. So basically, the setup is something like on the right hand side, in a very simplified way. So what this is called is a composite electrode. So it's like spheres of three types. So you have spheres of nickel on the anode side, spheres of LSM, lanthanum strontium magnetite, I guess, on the right hand side, and then you have this yttria stabilized zirconia, whose spheres are also like mostly in the electrolyte in between, but they are also spread across everywhere. So this is a composite electrode, and then you have a gas phase in it, and then there are surface of each of these spheres. So the species can exist on the surface of each of these two, let's say, different type of materials. So like electrolyte material and the electrode material. So electrode material is the metal material, and electrolyte material is the YSZ material. So yeah, you can see the list. So this mechanism has been taken from the paper of Tekalu et al. You can see there are five species in the gas phase, and yes, there are some surface adsorbed species. So subscript is like For example, HNI would be hydrogen adsorbed on the nickel surface, and Ni would be a vacancy. So it's an unoccupied space. Similarly, you have all kinds of things. So I would not read each of that. And for the electrical part, now we have a missing component because the model does not have the effect of charges of the particles. So what happens is for the charge, so we do not solve the middle part of this. So in the middle is the solid electrolyte, and what happens is these oxide ions would cross from cathode to anode, but that transport is not implemented in the model. So we take help of these simple equations. So you have, for example, so basically IV is the Faraday's constant times electron generation rate that gives you the volumetric current. You integrate it um, to get the current density, which gives you some continuity of charge to show that the circuit is closed. And yeah, and then you have simply the Ohm's law. So Ohm's law is active everywhere. We do account for the potential drop that this impervious electrode would create. Apart from that, now there are surface species of two kinds. So we have some evolution equation, like the rate equation for the change of surface concentration, one for the electrode, one for the electrolyte. So let's see how this performs. So yeah, in our test, this performs quite well. So I want to declare that this test does have a free parameter. So basically the thing is, because you do not model the flow in this solid electrolyte, you do not know how thick your active region is. So active region is like the length of the electrode uh, for which your electrochemical reactions are active. So that becomes like a free parameter in this case. But once you choose that one free parameter for one porosity, you do not change it. So we see these are polarization curves. So it's just voltage versus current. The more current you draw, the more drop you have in the voltage. And this is how Ann Birker had done a set of very good experiments with a lot of data. So we could reproduce it, and we see that we have reasonable agreement for three ratios of porosities. So 0.57, 0.48, and 0.32. And the right hand side is the same plot, but it's in power density versus current density. It's just the product of the axis. And yeah, and because now we have a good detailed simulation, we could also go inside and see what's really happening. So you can see that the top plot is the gas phase species. You can see that water is being produced. So the middle blank is where the solid electrolyte is. We do not solve. You see the water getting produced at the interface. You see hydrogen getting consumed, not too much, but still. Then you see oxygen getting consumed on the cathode side. Here also there are variations, but they are really small. These are the surface adsorbed species. Temperature also is nice. So you have anode side, so you have oxidation with which increases your temperature, and cathode side you have reduction reaction, which is associated with drop in the temperature. And then you have potential, so potential of anode, potential of cathode, and then this potential drop that is on the that is in the electrolyte basically. On the right hand side, you can see the volumetric generation of current, like amperes per meter cube, and then this is an integrated quantity basically. So the sign convention is chosen such that you integrate in a positive way than negative way. So if it goes from 0 to 0, yeah, sorry, 0 to 0, it's in balance, like the cell is in closed circuit. Yes, so yeah, coming to the last slide, we can do more in this. For example, study the effect of tortuosity as a parameter and I said multiple times. I think there is a very good scope of modeling ion transport. You can also model temperature in the solid phase, for example. You can extend this to multi-phase model and then do a PEMFC, for example. and you can validate two multidimensional setups. Yeah, so thank you for your time. And if you have any questions,
So, in the very beginning, you showed the validation of your method for different kinds of atoms and comparing to experiments that existed, right?
Yeah.
I was missing how the specificity of your various components is entered into the Boltzmann context, and what, if any, fitting parameters you have to fit that. Yep, what is the first? Yeah, exactly. That was a bit different. Helium, neon, and argon. Exactly.
So there are no free parameters in this setup as such, because uh, yeah, only the diameter of the capillary tube is known. It is entered as it is in D0. And yeah, this experiment is completely free of any free parameters.
You have to set various viscosities and stuff, right? So
Yes. Yeah, so that the viscosities are like average of the component viscosities, and there are some mechanisms like standard mechanisms like GRI 3.0. They have them, and some of them I constructed through Leonard-Jones potential, for example. Once the Leonard-Jones potential is known from some papers, then it's possible to compute the diffusivities and viscosities and so on.
okay, so you have those information from elsewhere and you edit them into.
Yes, yes. So there's a package coupled with this. I'm sorry, I forgot to mention, called Cantera. In Cantera, you can enter this Leonard-Jones potential. You can supply it some mechanisms, and it gives you what you want in terms of parameters. Thanks.
There is still time for a very big question, please. Just a little picture. You can see that at the low temperature, the error is relatively light. This may be due to the user number effect, because in this region, the micro stroke is very thin. So
Yes.
the number is positive neglect user effect, particularly for low pressure.
Yes, so that was this dusty gas model was supposed to take care of the Knudsen effect, but it seems like at 60 Pascal it's not good enough somehow.
You can consider the Lucent effect, Lucent diffusion, or something else.
Yes, thanks.
Yes.
Thanks.
Okay, thank you very much. The next talk, given by Manju Wan, and then it's about the evolution reactions redox flow batteries.
What is this?
It's the other way around. Sorry, it's the other way around.
It's the next one.
That's good. Thank you.
Okay, please go ahead.
Okay. Hello, everyone. My name is Kang Jundan. I come from Institute of Energy Technology of Fortune Center Jülich. Today is my great honor to show my investigation about parasitic gas evolution reaction in vanadium redox flow battery studied with the lattice Boltzmann method. In next few minutes, I will introduce my research background. What I studied is full vanadium redox flow battery. It becomes a promising technology since it's long lifespan, high reliability, adjustable power and capacity, and no operation and maintenance cost. As the name suggests, the energy storage medium is vanadium electrolyte. Here, I use the red color of vanadium electrolyte to represent the valence state. During the working process, the electrolyte is pumped into the cavity of the battery where the electrochemical reaction occurs and charge and discharge process is achieved. In the negative electrolyte, it has a valence of 2 plus and 3 plus, and in the positive side, it has a valence of 4 plus and 5 plus. From this perspective, it is only a change in valence state, and it should be a single phase environment in this system. So why there are bubbles in the electrode? Then we need to know what really happens in the porous electrode. On the one hand, it is very hard to achieve an ideal environment in this system because there are some residual air bubble during pumping process. On the other hand, the peristaltic reaction will generate bubbles in the electrode. And on the right side, there is a figure shows all related reactions in the vanadium reduced flow battery system. The normal working potential window is from -26 volt to 1 volt. We should note that during this normal potential range, there's still some unexpected side reactions, including the hydrogen evolution reaction in negative electrode and the carbon corrosion reaction in positive side. This side reaction will generate bubbles and reduce the effective surface area and block the transport of reactants. This phenomenon is particularly severe in the lactic side. However, previously, some researchers thought this overlooked this side reaction and assume that it can be ignored. Since 2010, because vanadium reduced flow battery becomes a hot topic, and researchers began pay their attention to side reaction. So they do the long-term durability test. From this current potential curve, we can find that as the working time increase, the current contributed by the hydrogen evolution reaction increases. As for the overall performance, there is a plot showing the capacity loss. We can observe that as the working cycle increase, the capacity loss increase significantly. So from these studies, it can prove that the side reaction couldn't be ignored in vanadium redox flow battery system. Later, some researchers want to figure out how the bubbles distributed in the vanadium redox flow battery system. Here is an experiment which can observe the bubbles distribution before and after HER. This is a schematic display of the experiment setup. The red box showing the scanning domain during the experiment. On the right side, this is the figures showing the bubbles distribution before HER. We could observe that there is already a lot of bubble in the electrode. And after HER, the fraction of bubbles volume increased significantly, and it occurs the obvious block accumulation region. However, even we use so advanced imaging technology, it's still very hard to identify the effect between microstructure and bubbles. So in my present study, I want to use the mesoscopic simulation method to investigate the bubbles transport behavior in electrode and find a strategy to improve the performance of battery. Firstly, I need to get the microstructure from synchrotron experiment. The resolution in experiment is 2.44 micrometer. The electrode used my study is carbon field. It has a very loose structure, and the original porosity is 0.95. In this experiment, we scan different we scan the electrode on the 3 different computation rates. I also show the related porosity in the right side table. I calculate the process distribution and compare it with the results from literature. They have a great agreement. Then I will introduce the simulation method in my study. I adopt a color gradient model to do the simulations, and this model is very suitable for immiscible two-phase flow. The density function is F. It can be divided into red fluid and blue fluid density. In my study, I use red fluid to present the electrolyte and blue fluid to present the hydrogen. The collision part includes 3 parts. In the first collision, it achieves a single-phase collision is same as the classical lattice-Boltzmann model. In the subsequent perturbation step, the interfacial tension generates by introduce the color gradient function. The color function is defined as the density difference between the 2 different fluids. The last step is recoloring step. This step is used to produce the phase segregation and maintain the phase interface. Then I will introduce my model setup. Here is a diagram showing the computational domain. At the inlet and outlet, I set a buffer region with the thickness of 20 lattice. It is used to animate the influence of complex geometry on boundary settings. The flow is driven by the external body force. It can be regarded as the pressure gradient. So I can use the acceleration to control the flow rates in this study. As for the reactive boundary, it is applied to all the fluid loads adjacent to the carbon fiber surface. It converts all lighting populations of one fluid species into another. It is governed by the reaction rate Kr. Normally, it is determined by the local current density, and it is set as a constant value in my study. In order to have the bubble remove the computational domain, I use the recurring boundary at inlet and outlet. This boundary can recolor the population entering the boundary region with a specific ratio. In my study, this ratio is determined by the initial fluid density. Then I will show my preliminary results. First, I investigate the effect of a reaction rate. I choose 3 different magnitudes. The lowest one is chosen from the current density from literature is around 5 milliampere per square centimeters. In order to quantitatively analyze the bubble screws, I calculate the electrolyte saturation and the bubble coverage. The bubble coverage can reflect the loss of effective surface area. Let's see the case with lowest reaction rate. We can find that the bubbles are observed on the carbon surface and could only dissolve from the surface once they grew to a certain size and then move under the influence of flow. If I increase the reaction rate to the middle value, we can find that some bubbles are merged together and become blocked by the carbon fiber and then move again once they reach a larger size. If I increase the reaction rate further, we can find that there is a obviously fluctuation in the electrolyte saturation curve. Each fluctuation can represent the fusion growth and the removal process of the bubbles, which are difficult to be removed in the computational domain. The amplitude can represent the size of this kind of trapped bubbles. Overall, we can, as the reaction rate increase, we can find that the bubble size in the computation domain increase and the frequency of bubble being removed increase. We can get the results that our goal is to suppress the occurrence of hydrogen evolution reaction because it can lead to the uneven gas release, which has a bad influence on battery's performance. Then we began to investigate the removing method of bubbles. The factor is acceleration, which is I mentioned before. Firstly, we can see the case with the lowest acceleration. The electrolyte saturation decreased monotonically. And from the bubble coverage curve, we can find that there is a plateau stage. At this stage, bubble size is not large enough to reach other bubbles and carbon fiber around. and then it enters a rapid increase stage. At this stage, it is mainly caused by the phenomenon of encapsulation. If I increase the acceleration to the middle value, you can find that the occurrence of acceleration decrease, even though the electrolyte saturation doesn't change a lot. Then I increase the acceleration to the largest value. We can find that the bubbles carriage can reach a stable state, and there is also a significant increase in electrolyte saturation. So we can know that there should be a optimal flow rate in the operation, which can remove bubbles efficiently, but reduce the external pumping energy. Then I investigate the effect of microstructure. From the electrolyte curve, we can find that as the compression rates increase, the rate of gas generation increase. This is because the fiber stance increase if we increase the compression rates. And then from the amplitude of this of the fluctuation, we can find that the bubble size increase as the compression rate increase. And from the bubbles coverage curve, we can find that when the compression rate increase from 25% to 50%, there is a slightly increase in bubbles carriage, but when we increase the compression rate from 50% to 75%, it have a significant increase. We also did some investigation on diffusivity and conductivity. In our previous work, we find that there's a positive influence on conductivity. So it's very interesting to do a comprehensive study on these all properties on batteries performance. This is also my last research. Overall is all of my preliminary results. Firstly, we analyze the bubbles formation and the evolution process in porous electrode, and also compare the different factors on bubbles behavior. In our last study, we want to consider the advection diffusion model to investigate the bubbles on the overall cell performance. Thanks to my co-supervisor Michael Eichling in IET3 and Professor Yeshartin in IET2 and Professor Josvita Sas in FAU, and also thanks to the other members in IET3 and the HIU's group. Thanks for your attention.
Questions? There's already the ball size is getting bigger.
Yeah.
I'm just curious, there are possibility just keep this ball size.
If the reaction rate keep a low value, it's possible, but if the bubbles can dissolve from the carbon fiber surface, when they move under the influence of flow, they have a high possibility to merge together and blocked by other fibers. Yeah. It's hydrophobic. Yes. We did some investigation about the wettability, but normally we will keep it in the region of hydrophility. So it has a very slight influence on the bubbles behavior. Welcome.
Okay. So there's lots and lots of parameters in your system, right?
Yeah.
And I'm wondering if the picture that we saw are, the generic one or are the ones that you always get. I mean, you could imagine all kinds of other morphologies. You could get these big connected domains. You could get all. So is that a very typical appearance that you get, or can you get all kinds of other morphologies in your simulations?
Because the domain size is not large now. So actually, this is a good question. Maybe if I enlarge the domain size, I can observe other bubbles morphology. In the later study, I will try to use larger size. Yeah, thanks for your question.
I was just asking about this carbon structure. A lot of these carbon structures have like a binder material that binds the carbons together that has different wettability properties than the carbon fibers.
This is
State.
Consider that. So there's only carbon fibers because no binders, only carbon fiber. Because in vanadium reduced flow battery system, we activate the electrode by thermotreating method. So there's no other catalytic material. Yeah. That's also the reason why we want to compress the electrode, because if we only use the original carbon field, it has a low conductivity.
Let's thank the speaker again. And then it's relevant to hydrodynamic modeling and simulation of crystallization reactions and parallel sensitivity analysis. Thank you very much.
All yours.
So welcome everyone to my talk. I think that people who have been to the latest Boltzmann session by ECOMAS in Portugal have already seen the first part of my talk. And yesterday I already recognized that it will be somehow similar to your talk about sensitivity analysis and saturation in the porous media on the nanoscale. And the whole idea of the story is that my PhD topic is phosphate recovery from the wastewater, so that it can be reused in the agriculture or phosphate industry. And it's recovered by adsorption reaction on the surface of the calcium silicate hydrate or CSH particles with the following reaction. It's an ionic reaction that happens in the pores on the nano level by reacting of calcium, hydrogen, and phosphate ions to octocalcium phosphate as precursor to building of hydroxyapatite crystal. And my goal is to find the sensitivities or the main influence factors and how strong is the influence of these factors on the whole reaction. First, I already simulated the adsorption on the macro level. What is not so efficient? I mean, it's possible. I also have done it with lattice Boltzmann and made a publication about that. But the problem is that if you simulate adsorption on the macro level, we just represent adsorption with a mathematical approach, with like this adsorption isotherms that were taken experimentally for each species. And I could not really investigate the influence factors on the reaction itself that are acting in the pores. And that's why I went from the macro level to the pore level, which in that case it's nano level, because one pore is in the CSH particle like in average size of 40 nanometers. And it's like model how it works now by me. I have the pore resolved with Knudsen number 0.1. So I assume slip boundary condition for the carrier fluid flow at the surface. I have calcium desorption or dissolution reaction under action of hydrogen ions, and I have then reaction of calcium ions, this dissolved calcium ions with hydrogen ions and phosphate ions to octocalcium phosphate. And I also assume the Helmholtz plane like a surface potential. And the problem is that I don't really know which surface potential I have that on this microparticles. And how the surface potential is changing during the reaction, which is why I will just investigate two cases. One is with negative potential, other with positive potential. And this is the full equation system. We have carrier fluid that is solved with standard Navier-Stokes equations with electric force. Then we have reacting ions that are solved with Nernst-Planck advection diffusion reaction equation with also this electric velocity. Then we can calculate from the potential difference. We have three ions, it's hydrogen, calcium, and phosphate, so three advection diffusion equations. And we have electric potential that is solved with Poisson equation for potential distribution, and it has an influence on the Navier-Stokes equation and on each advection diffusion equation. This is my ionic reaction system. I have a solid surface of CSH that dissolves under action of hydrogen cations, the calcium cations, and then the second reaction of crystallization. In sense of reaction kinetics, it looks like that. I consider activities of ions, not directly concentration of ions, but they are activities which I'm calculating with this, I think, Debye expression. In the current talk, I'm interested in the sensitivity analysis, and the main factor that influences these reactions is the saturation product of the octocalcium phosphate, which I'm investigating and which I'm tracking through the whole reaction, how it changes according to changing of different parameters. The whole system is described with the lattice-Boltzmann equations. I would say it's in that topic nothing new. The standard BGK collision operator, standard Guo forcing approach, and the only thing, and this Poisson equation for electric potential, I'm resolving on that way that I assume that my diffusion constant is 1. I have no temporal derivative, and I just can solve the internal loop of Poisson equation till the convergence. And the positive thing is that in case of Poisson equation, I can calculate gradient directly by taking the first moment of the Poisson equation population and not making a finite difference and taking in account the neighbor cells. That's why I can solve the whole system on the GPU. If I have like a huge microparticle, if I have resolved, then I can make the whole study on the GPU, what I've done on our Horeca cluster in Karlsruhe. This is a full simulation loop. First, I calculate the Poisson equation, then I make the Navier-Stokes Collider stream step, then the 3 Nernst-Planck equations for each ion. Then I have the so-called post-processor in OpenLB, which calculates reaction rate, saturation products, if the cell is solid or not. Then the next time step comes. And to calculate the sensitivities, we have in OpenLB the automatic differentiation algorithm, where the standard derivation rules and the derivative combination rules are directly programmed within. And now each population and practically each variable in the whole simulation code is now a vector that consists of the main variable itself, like just Boltzmann population or some other variables, and the derivatives which come after that in the vector. Which is why the simulation becomes less efficient, because you solve instead of only one like number per variable, you solve the whole vector. but you directly have the sensitivities without making finite difference, like of different simulations, without making multiple simulations directly with that. And I also compared in the graph the automatic differentiation with finite difference method. The finite difference method gives different results according to and dependent on the this parameter that you are variating of the cells, not cell size, but this parameter size, but by all of them, it like it shows the same behavior like automatic differentiation method. And I applied the whole code to the resolved porous media, to this microparticle. First, I made 2D simulation and then 3D simulation. On the 2D simulation, I investigated two types of pores. It's like open pores and blind pores with fixed velocity at the outer corners of the simulation domain, fixed hydrogen phosphate concentration, and zero gradient of calcium concentration because calcium is generated on the surface of the particle itself. For potential, I have zero gradient, and I have full slip for velocity, for carrier fluid velocity on the particle surface. And this how looks the development of the maximal saturation product in this 2D systems. We can see that in the blind pores, the saturation product is twice higher. And as I said, I investigate two cases of the surface potential. It's one negative and one positive. And we can see that in the case that positive surface potential leads to higher saturation product. And the derivatives that are stored in these vectors give us like a dependency of maximal saturation product of this size of the surface potential. And we can see that in the blind pores are more dependent on the derivative of the to surface potential as the blind pore is higher, and the positive potential. I mean, we can take higher positive potential to achieve higher saturation product in the deepest point of the blind pore. Then this is the derivative to hydrogen ion concentration. Logically, is if you have more hydrogen, then you have like higher possibility of crystallization. The same story with phosphate ions, that you have more phosphates, and you have also higher saturation. And this is the interesting plot that you need deeper pores to achieve higher saturation, because like the whole calcium that is generated on the surface of these deeper pores, it's under action of the positive potential. It's stored or it's accumulated towards the end of the blind end of the blind pore. And at that point, you have then higher saturation product. And also the diameter of the pore should be smaller, so that the pore has a big surface area in comparison or relative to the pore volume. And the inlet velocity has like a random. In the case of open pores, the inlet velocity is always bad, because it moves the ions away from the points where they are accumulated, and you have less saturation. But in the case of blind pores, if that blind pores are open towards the dead zone of the flow, at some cases it can be the saturation can be higher. And on this derivative to the inlet velocity, we can also see the point when the pore is maximally filled with the species. Is this maximum after which time point the derivative falls, because the velocity starts just to flow or to push away the accumulating ions. And here are the conclusions to the two-dimensional case that blind pores accumulate more ions. Higher surface potential leads to higher saturation. In most cases, the concentration of hydrogen and phosphate should be higher to achieve higher saturation, what is logical. Deeper and narrower pores store more octocalcium phosphate, and inlet velocity promotes faster pore filling, but after that, it deteriorates the saturation products. And the same story with three-dimensional geometry is the slice that's in one plane in the middle of this three-dimensional micro CT scan. It's how the saturation product is distributed itself. In that case, it still doesn't reach value of 1 to start the crystallization, but we just can see where is it higher, where is it lower. We can see that it's high only in some pores that are in that case blind. We have practically very low saturation product at the outer surface of the particle itself. And after that, what we can say that whole saturation happens inside of the pore, inside of the particle towards the center of the particle at the deeper pores. Here in the derivative to the Helmholtz surface electric potential, we can see that in the pores where the saturation is higher, also the derivative can be taken higher because these are blind pores and the deepest blind pores in the current geometry. The derivative to the inlet velocity shows us this strange behavior because the velocity goes from left to right. And so that means that we have the dead zone of the flow. In this dead zone, phosphate and hydrogen are accumulated, and the blind pores which are open into the dead zone, they accumulate this phosphate and the hydrogen. But in the big real geometry of in the full microparticle of CSH, this velocity inlet carrier fluid velocity influence would be really random. And saturation to hydrogen concentration and to phosphate concentration shows the same as in the 2D case, that if you have more phosphates, acids, then the saturation of it in the pores will be higher. And this is also interesting thing that I simulated 2 different cutouts of this pore geometry, and in the bigger simulated particle, the saturation is higher because I take more pores within the simulation, which in the summarized length of the pores is bigger than in the small geometry, and that's why it accumulates more calcium and more octocalcium phosphate in the center of geometry. And these are conclusions for the 3D geometry. The blind pores accumulate more, as also said in the 2D case. Higher surface potential leads to the higher saturation. And interesting thing that this positive derivative with respect to the surface potential, we have only in the blind pores. It means that there's only if the pore has one outlet to the bulk and one pore and or multiple blind dead ends. It doesn't matter. It always has in the current case positive sensitivity. If the pore has more than one exits to the bulk, it has negative sensitivity, and on that it could be like a way how to evaluate the micro CT scans also. But if you have scan, you make this simulation, and you can it will be relatively quick, and then you can just visualize only blind pores and separately open pores. This concentration of hydrogen phosphate should be higher. Inlet velocity increases saturation occasionally, depending on where the current pore has its exit, and if in that place you have that flow zone where this hydrogen and phosphate ions are randomly accumulated in that case. And to fully understand which saturation product and at the end which crystal volume you will get in the particle, you really need to resolve the full particle or take some assumption, because as you see, if you take a bigger simulation domain, you have like bigger summarized length of the pores, and which is why higher saturation product, more crystal, and so on. And yeah, in these pictures, I think I visualized the blind pores, only blind pores and not the open ones. We can say that with the current electric model, we can simulate the nanoporous 3D system. Yeah, under assumption in the current case that Knudsen number is lower than 0.1, but we can also resolve it finer if we add Knudsen diffusion. It is also possible with Lattice-Boltzmann. Sensitivity approach gives us directly, I mean, the automatic differentiation approach gives us directly the sensitivities, and we don't need to do a lot of different simulations to make like finite difference method. Yeah, I validated that they both give similar results. Considering the current case of phosphate crystallization, blind pores accumulate more ions, positive surface potential. It forces ions to accumulate deeper into the blind pores, closer to the dead end of the pores. Narrow, long pores accumulate more ions than the open wide pores, and carrier fluid velocity really occasionally increases saturation. We cannot say that if we increase the rotation frequency of the mixer, it will be everything fast. And I also validated the whole equation system on the analytical example. I just didn't show it here. I have analytical solutions for like this 1D Poisson-Boltzmann equation and practically the Poisson equation itself. And electroosmosis, at which I validated all of the equations, and they showed convergence order of 1. Yeah, thank you very much. And if you want, you can join the next spring school in Marseille.
Questions? You simulated, or you can Dscan of a real particle?
I just found the CT scan in the internet is the carbonate astylates of some British university, but we have measured pore size distribution in the calcium silicate hydrate, and then I just I had this pore size distribution in the scan that I found, and I just scaled down this scan to the size so that I have the same pore size distribution. For boundary condition for what? For the pore surface. At the pore surface, I have full slip condition for the carrier fluid for the Navier-Stokes equation. I have 0 gradient for advection diffusion equation, and I have Dirichlet boundary condition, like fixed value for the electric potential.
Well, related to that, so why do you have full slip, and how would the result change if you had a non-slip boundary condition? And I mean, what the
okay, I also investigated that. First, why full slip? Because I think by Knudsen numbers between 0.1 and 0.01, you have full slip for the carrier fluid, for the Navier-Stokes equation. And how it will change, the velocity itself has less, the carrier fluid velocity has less influence on the ions or the movement of ions than the electric forces. And that's why it will, of course, change like some percent of the whole velocity, because I also evaluated in the paper that I want to publish like this summed up velocity, where I summed like carrier fluid velocity plus electric velocity plus diffusive velocity, and the electric velocity was the strongest one, much stronger than the carrier fluid velocity influence onto the ion movements. And that's why it will, of course, change in some sense, but not radical. Yes, I also, yeah, but the problem is I've implemented the simplest nucleation model which considers also surface tension. It's like it's a big expression where you have the saturation product and surface tension. And yeah, but the problem is that I could not really validate it. I have programmed that it's implemented in the code, but I also simulated the growth of crystal. But I cannot say that it's absolutely correct. That's why I didn't want to show it. Yeah, the classic, absolutely the standard nucleation, and after nucleation has reached the value bigger than 1 divided by the volume of cell, I assume that in the current cell there is 1 nuclei that starts to grow. For nucleation, no. I just taken like some simplest formulas that I found in the book, and, and that's why I also didn't show it. But it's implemented. But as I said, I not really validated, and I said, okay, influence sensitivities to consider to sensitivities applied to saturation product are enough for the first attempt, and that's it.
There's probably a question about the sensitivity analysis and the auto differentiation. So if I understand well, you solve one case, and then at the same time you have the sensitivity analysis around that case, right?
Yes.
Test for all kinds of conditions and things. You will need to run.
Of course, if I want to test the sensitivities under other boundary condition or values of the condition, of course I need to make a new simulation. But I mean, I already get all the sensitivities. And yeah, as I said, in the current case, it's forward automatic differentiation, I think it's called, and you always then store a vector of variables, and that's why you deteriorate your efficiency. But I mean, you lose an efficiency, but you don't need to make multiple simulations with the same boundary condition. Yep.
Other question, please. Next question. Can move to the next presentation. Yeah.
There is a pointer? No. Okay. Good morning, everyone. My name is Maria from PUC University in Brazil, and I'm here today to talk a little bit about a recent work with Professor Felipe here about a Lattice-Boltzmann model for immiscible fluids with non-unitary molecular mass ratios. So firstly, I'll introduce a little bit about how models usually set a non-unitary density ratio for in the literature. I'll give a quick overview of the model we were working on, and then show some results for some benchmark simulations for validations and some initial simulations trying to reach a Taylor instability. So how to set a non-unitary density ratio? We identified two main ways of doing so in the literature. The first one would be by working with a no-ideal equation of state, basically changing proximity of the particles done by a forcing term, for example, like in a pseudo-potential-like model, or adding a source term directly in the Boltzmann equation, introducing an excess pressure or an excess chemical potential. The second way would be by working with different masses for each component. Usually, one of the first things these models address when working with with different masses for each component would be the difference in velocities. So for a given temperature, a heavier component would be slower than a lighter one. In 2005, McCracken and coworkers divided this model in two groups. So I'm adapting this division here for the review. The difference lattice speed approach, as the name says, works with different discrete lattice velocities for each component depending on its mass. So for a single time step, each component would travel through a different distance, and that would require interpolation, a spatial interpolation between mesh nodes or a temporal interpolation, and that could add some errors in the calculations. And the second approach is the same lattice speed approach, which models focus on recalculating the equilibrium distribution as a function of the mass ratio. There are a number of ways of doing so. One would be by recalculating the constants in the equilibrium distribution. And one of the consequences of that is changing the weights for each velocity. So a lighter component would have a higher tendency to acquire higher velocities and so on. Some authors also choose to control only the rest particles. So a heavier component would have more rest particles and that would slow it down. What we are proposing to do is to work with the same lattice speed for all components, but adding a mass parameter. So consider a reference mass related to the mean molecular velocity. And for the Maxwell-Boltzmann equilibrium distribution, for generic P fluid, when making this function dimensionless, a mass parameter appears naturally. We're calling it here RP. We're calling it RP. And it's basically a dimensionless mass. We are applying this throughout the model and the model's discretization. So far, we've working with another parameter model based on the works of Constantson and co-workers from 1991, but applying some relevant modifications found in the literature as the segregation rules proposed by Latva, Koch, and Rothman in 2005 that enables to control the interface thickness. We're also adding an Ensgog volume correction in the equation of state and working with the heuristic interface tension source term that has been adapted by many authors since it was first proposed by Constantson. Starting here from the Boltzmann equation for this generic P fluid, we are applying a simple relaxation BGK collision operator, and the source terms there are for the gravity, the volume correction, and the interface tension. Note that the distribution function for this individual P fluid is based on the number density of particles. But consider now a mixture of a binary mixture of a P component and a Q component. To allow cross collisions to happen naturally in the interface region, we are applying it in a blind distribution that won't distinguish P particles from Q particles. So we are defining this blind distribution as the sum of each individual distribution multiplied by its dimensionless mass. So the moments for this blind distribution function are based on the total mass density, total linear momentum. And here in the second order moment, we find the total ideal equation of state based in the numeric density of particles, total numeric density of particles. We are working with a third order discretization scheme for the velocity space, applying a D2 V17 velocity set, as illustrated here in figure 3, and which results in equation 7 for the equilibrium distribution of the P component. Note that there are second order and third order terms depending on this dimensionless mass. The discrete source terms are given by equation 8 for the gravity in terms of the weight and the buoyancy, for equation 9 for the volume correction in terms of the excess pressure, and by equation 10 for the heuristic interface tension, where phi here is the order parameter and En is a vector normal to the interface pointing to the P component. For the discrete implementation, we are applying a mixed scheme for the discretization of the advective term. So we are applying a second order discretization only on the gravity and volume correction source terms, and a first order discretization on the rest of the terms. After collision, given by equation 12, in the blind distribution function, we need to tell each component apart. So we're applying the segregation rules proposed by Latva, Cook, and Rothman. And it's where we set the interface thickness, which is inversely proportional to the B beta parameter right there. After segregation, we can go on with propagating and recalculating all the terms necessary for the next time step. With this, we retrieve all the expected macroscopic equations, where in the linear momentum balance there, the P is the non-ideal pressure. We are working so far with a simple van der Waals equation of state, considering setting the interparticle attraction to 0 to avoid phase transition. And the tensor S there is related to the interface tension. For the simulations, we started with a simple plane interface. So here we have the results for a mass density profile in the interface by the normalized position. We have the results for various simulations varying the interface thickness parameter, the segregation parameter beta, in comparison with the theoretical prediction given by Helmholtz free energy. In black, we have the total mass density, in blue, the Q component mass density, and in red, the P component. And as you can see, they're all adequate fits. We also got good results for the Young Laplace test, varying both the mass for the P component and the segregation parameter beta. All simulations followed Laplace's law. For the layered Poiseuille flow, we evaluated mesh refinement. So here we have a fully developed linear momentum profile for the normalized linear momentum by the normalized position for 3 different meshes in comparison with the analytical solution given by Navier-Stokes equations, the solution of the Navier-Stokes equations. And they're all adequate fits, but as you can see, the higher as expected, the more refined mesh gives a better fit. And for the Taylor instability, we initialize the simulations with the upper half of the domain field with a heavier component and the lower half with a lighter component, introducing a perturbation given by equation 24 in the interface, and applying an acceleration pointing downwards. The boundaries are periodic in the left and right, and bounce back non-slip, halfway bounce back non-slip on the top and bottom. Usually, Haley-Taylor instabilities are described in terms of the Atwood number, comparing the densities for each component and the Reynolds number. So here are some results for a Haley-Taylor instability with a 512 Reynolds and 0.15 Atwood number for a 128 by 512 mesh. We got the expected jet going downwards, the characteristic mushroom shape, the formation of plumes going upwards, and in the later time steps, we have the appearance of some plateau Haley instability, where the thinner parts of the plumes collapses, leaving a trail of small droplets behind. And here for the same, keeping the same Reynolds and same Atwood number, but for a more refined mesh, we can see the evolution of the exact same stability, but with some, we're able to visualize some greater details. So far, we are working with some relatively low mass ratios, but that's because for the static condition, for a static initial condition, the equilibrium distribution function for a D2 V17 velocity set is only greater than 0 for a dimensionless mass lower than 1.098. But we have reasons to believe that that can be solved with a higher order discretization for the velocity space as a D2 V37 velocity set, as the fourth order terms in the equilibrium distribution would eliminate this restriction. As in the literature, the density ratio can also be increased by considering the interparticle attraction in the equation of state different than 0. That's the next step we're working on. And lastly, we've noticed that the segregation parameter beta, or the interface thickness parameter beta, seems to be interfering in the displacement, the full dynamics of the interface. But we need to conduct some further testing to verify that. That was it for now. Thank you for your attention.
Advantages of this one over recent color gradient models, which can also do higher density ratios. Is there a difference?
I'm sorry, I didn't get the last part.
There are recent color gradient models which can also density ratios, not all the steps. Is there a difference between your and the other?
Oh, we are just recently evaluating adopting different masses ratios, but it's all very recently. We're all still testing it, and we can further. We hope we can further increase the density ratios as well.
They also do the same thing as mentioned, and they correct for the pressure in the denser phase like in their own words.
Thank you.
So in this approach, what limits your mass ratio? What's the mechanism that makes it presumably unstable if you try to choose too large a mass ratio?
The equilibrium distribution, it's only greater to 0 for a lower masses, like 1.098 as. For a static condition, where we set the macroscopic velocity to 0, the equilibrium distribution will only be greater than 0 for this condition.
Where does that go into the equilibrium?
I'm sorry, theta p is inversely proportional to RP. So there's a divided by RP there.
Thank you.
It's periodic. It's periodic boundary condition in the left and right sides.
Okay, so, any further questions? This is the case, let's thank our speaker.